So we've been talking the whole time, and you've heard me say it like 100,000 times. Well, probably not that much. But what we do with exponents is one level below what we see. When we saw exponents, we multiplied. When we saw the level of addition subtraction, we did nothing, which was the reason why they had to be the same. The exponents had to be the same in order to perform that operation, because we do nothing with them. When we saw multiplication, we added. Now, what do we do when we see division? Well, if we're doing one level below what we see, below exponents is multiplication, below multiplication is addition, below addition subtraction is nothing, below division, below multiplication is addition, below division would be subtraction. So it seems logical that if we add exponents when we multiply, we should subtract exponents when we have the inverse of multiplication or division, and that's exactly what we do. So when we see division of common bases, what we do with the exponents, well, we subtract them. Now, remember a couple things about this. Exponent rules only apply to exponents. So what do we do with the bases when we're doing exponent rules? Nothing. We don't do anything with them. They stay exactly the same. So when we have b to the m over b to the n, we can keep our b and we can subtract our exponents. Notice what we don't want to do. We don't want to get 1 all the time. We don't want to do anything with that base, because if we divided the base itself, you'd always get 1. And then 1 to any power would be 1. That's not logically correct right there. So what we're doing with the exponents is we're seeing division, subtracting the exponents. It works all of the time when we have common bases. So 6 to the 9th over 6 to the 7th, we can do not 1 to the 2nd, because we don't want to divide our bases. You'd always get 1 that way. We'd get 6 still to the 2nd power. Now, of course, you're going to question, why does that even work? Well, think about what's going on here. We really have 9 6s being multiplied. Over 7 6s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. We can simplify 7 pairs of 6s each time, giving us an actual 1. We're literally dividing here. So 1 times 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 6 times 6. There's not enough 6s on the denominator to match up with all the 6s on the numerator. Otherwise, we would have gotten 1. Otherwise, we would be dividing something by itself and actually getting 1. But our numerator outpaces our denominator. That's an important concept in the scheme of what we're about to do. So our numerator is larger than our denominator. That means there's more 6s being multiplied up there. That means that when we simplify, the remaining 6s are going to be on the numerator. That is how the exponent rule works here. That's how the quotient rule for exponents work, is when we subtract, we're always getting something that's implied or inferred to be on the numerator. Now, if that's a negative exponent, yeah, we'll have to move it back down. But that's the way this operation works. We subtract exponents, it's on the numerator, over 1. That's how it's always done with this particular rule. So the reason why it works is we have a certain number of this base over a certain number of the same base. They're going to pair up. They're going to start simplifying, and what we're left with is that base raised to whatever the difference is between our exponents, numerator minus denominator. Remember, subtraction is not commutative, neither is division. So the order is very specific on what we do. Top exponent minus bottom exponent, no matter what they are. And that gives us 36. Same thing with variables. Hey, we have common bases. We're seeing division. What we do is one level below, we should be subtracting exponents. So here's the way this works. Now, well, wait a minute. This would be 5x's over 7x's. They still do simplify. X over x gives you 1 for 5 pairs. But notice how I still have 2 x's on the denominator. Wait a minute, what's left on the numerator? Nothing. Ooh, not nothing. You could always have 1. So we should get 1 over x squared. And that's exactly what we do get. But wait, how's the subtraction of exponents actually work with this? Remember that this rule is order specific. So when we see common bases, can we always subtract exponents? Yes, but in a very specific order. So this would give us x to the top exponent minus bottom exponent. 5 minus 7 is negative 2. Is this the same as this? If you watched the last video, you know it is. This is why we had to cover negative exponents before we got into division of exponents, common bases with exponents, because you get a lot of negatives here. With this rule, if you're going to subtract exponents, well, hey, if your bottom exponent is larger than your top exponent, you're going to get a negative. So a little recap here before we do the last step. What you do is one level below what you see, even with division. We're subtracting, but the order is specific. Top minus bottom no matter what. Now the logic behind it is, if you have common bases, you're going to get a lot of simplification. Where your higher exponent is where your factor is going to end. Let's say that one more time because it's got to sink in. Where your larger exponent is where your factor is going to end. If your larger exponent is on the numerator, you're going to have your base on the numerator when you're done. If your larger exponent is on the denominator, you are going to end with your factor on the denominator when you're done. Now, the last thing, what I had to get you to get, is that when you're doing this particular rule, what you originally get through subtraction is always on a numerator. So when we look at x to the negative 2, where is that? Numerator or denominator? It's always on the numerator when you do this rule. So if we're going to do x to the 5th over x to the 7th, and you're going to show me subtraction, x to the negative 2, 5 minus 7, that's fine. But this is always inferred to be over 1. Always. So then you move your negative exponent. You go, wait a minute. Last video, that's wrong. That doesn't look right. You're right. That x to the negative 2 is a factor with the negative exponent. It means 1 over x squared. So no matter how you do it, whether you're going to subtract exponents or do simplification, and both ways are correct, you're going to end with a factor wherever your larger power was. So larger power denominator, factor on denominator. Larger power on numerator, we're going to find this factor of y going to be on a numerator. So let's look at that problem. There's really only 2 more. If you want to go ahead and do them, now's a great time. But I do need to show you what to do with numbers. So let's check this one out. There's a couple things I really need you to understand that are really relevant. Firstly is this. When we're doing all of our exponent rules, especially with division, we can look at them as certain common bases. So we're going to separate these ideas in our head, working with the numbers, then working with each individual variable as a pair. And we can do that. You see, when we have this product and product, we can really think about this as 16 divided by 4 and y to the 5th divided by y to the 3rd, and we can separate this. So you could really think about this as 16 over 4 times y to the 5th over y to the 3rd. And you can do that with every single factor. If you think back to multiplication of fractions, this is true, because if you multiply fractions, it's just numerators go on the top, denominators go on the bottom, which means you can separate it, which is awesome. So we can view division as just a product of the different factors being divided. That's great. That helps us to apply these rules a lot nicer. The second thing, exponent rules only apply to exponents. That's all they ever apply to. So the reason why I'm separating this is for 2 reasons. First, it makes it easier to see the variables line up and the numbers line up. Secondly, when you look at 16 divided by 4, I don't want you to apply exponent rules to that problem. So when you do 16 divided by 4, I'm begging you, don't give me 12. Yes, you subtract exponents, but those don't apply to your coefficients. So when you do 16 divided by 4, you're literally doing 16 divided by 4. You're just going to give me 4 times. So this is 4 times, well, how about y to the 5th divided by y to the 3rd? Oh my gosh, I'm seeing division. Exponent rules only apply to exponents. If you're seeing division with numbers, man, divide them. But if you're seeing division with common bases and you're looking, what do I do with those exponents? One level below division is subtraction. You need to subtract them. So this is y to the second power. 5 minus 3 is 2. Notice the other way to think about this. There's 5 y's here. There's 3 y's here. Where are there more y's? On the numerator or on the denominator? Well, there's more y's on the numerator. You're going to end with, after simplifying, if you understand this idea of pairing them up, you're going to end with 2 y's that are left unpaired, unsimplified on the numerator. That's where more of the y's were. Now, Exponent rule works just as well. 5 minus 3 is 2. It's not negative. It looks really good. It's just 4y squared. There's no negative exponent, so we have to move nothing. So what we're doing, we're subtracting. Where the larger power is where your final answer is going to be for every factor. So more 6's on the numerator, answer is going to be on your numerator. More x's on the denominator, answer is going to be on your factor is going to be on the denominator. More y's on the numerator, your y's are going to end on the numerator. Divide your numbers, do not subtract them. Exponent rules only apply to exponents. Last one, we can do the same exact thing no matter how many factors we have. So I'm going to encourage you until you really get the hang of it. Split it up. That's perfectly fine. That way it kind of clues your mind into this idea that you're going to do 3 things here. You're going to look at every pair of factors, and you're going to do the appropriate operation. So when we look at 28 divided by 7, there's no exponents there. We're not even dealing with exponents. We're just dividing. So don't let your exponent rules influence your division of numbers. 28 divided by 7 it's just 4. I promise you don't get 4 all the time, just coincidence. But 28 divided by 7, that's 4. Times x to the 6th divided by x to the 3rd. 2 ways to think about it. Number 1, we could just subtract them. We're seeing division, what we do with exponents. As we'll know below what we see, you can subtract 6 minus 3, you get x to the 3rd. No problem. You could also think about it in the simplification way. Hey, you got 6 x's up here. You got 3 x's down here. You're going to cross out 3 pairs. Where are there more x's? Well, there's more x's on the numerator. So you're going to cross out 3 pairs, but you're going to be left with, and a lot of people show it this way, you're going to be left with 3 x's on the numerator. Are we still subtracting? Of course you are. You're matching up pairs, and you're subtracting off the pairs from the larger exponent. That's what we're doing. It's just that you need to understand that answer's going to be on the numerator. So x to the 6th, cool. X to the 3rd, 3 pairs. Subtract them, you get x to the 3rd on the numerator. Now, what about the y's? There's 2 ways to think about them. I'm not going to tell you either one's better than the other, okay? Because a lot of people do them different ways. But if I were to do this subtraction-wise, we'd have y to the, 2 minus 7. That's negative 5. So that's option 1. It's just divide, subtract x to the 3rd, and subtract. 2 minus 7 is negative 5. That's fine. Or if we divide and get 4, do our little cross-out method, simplification, get x to the 3rd. Or you could also do this. If you have, think about your fraction, just focus on y squared over y to the 7th. You have 2 y's on the numerator. You have 7 y's on the denominator. Where are there more y's? Because wherever there's more y's, that's where your answer is going to end. So if we have 2 pairs, so y squared y to the 7th, you can write it out if you want. You're going to match up 2 pairs. There's still 5 y's unaccounted for in our matchings, in our simplification. Those 5 y's are going to remain on your denominator. So if you want to simplify it that way, that's perfectly fine too. Well, there's 2 of them here, they're going to simplify. The 2 of them there are going to simplify with 2 of them on the denominator, leaving you 5 on the denominator. Are these different? The answer is no. We know that negative exponents mean I'm on the wrong side of a fraction. We know that y to the negative 5th power is 1 over y to the 5th. It's the same stuff, guys. It's the same exact stuff. So if we're viewing these as division and subtraction of exponents or division and simplification of exponents, it's the same stuff. Our final answer in either case is going to end with our factors with positive exponents on the numerator, and factors with negative exponents on the denominator. Factors with negative exponents are going to change sign when we move them to a denominator. So we leave the positive exponents where they are, we move the negative exponents to where they need to be. Here, if we did it simplification ways, we're already going to have that factor with a positive exponent. We have our factors on the numerator, factor on the denominator. Either way, we get the same answer. I'm really hoping this is sinking in. The exponent rules do still apply. Now we have negative exponents. There's two appropriate ways. Neither is really better than the other to deal with this. The first way is subtract. You can always subtract your exponents. Just keep in mind, whatever you get starts off on the numerator. If you get positive, you leave it. If you get negative, then you have to move it back to a denominator. Or we can simplify every pair of fractions. So every single pair of factors here. Divide numbers, don't let exponent rules accidentally overrule you on division. We can simplify, and wherever your larger power is where your factor is going to remain, where your factor is going to end. So if we have more x's on the numerator, your answer is going to be on the numerator. More y's on the denominator, your y's are going to be on the denominator with positive exponents. That's the idea. Now there's three other rules I want to show you. Not tricks, but they can really make your math a little bit better. Remember that what negative exponents say are, I'm in the wrong place. So if I have 1 over b to the negative n, that's saying, hey, I'm not supposed to be on the denominator, guys, move me. That would be b to the positive n. Whenever we move a factor from where it is in a fraction, it changes the sign of the exponent. So whereas b to the negative n meant 1 over b to the positive n, 1 over b to the negative n means b to the positive n. We can always do that. That means that 1 over 5 to the negative fourth power, well, that's really 5 to the positive fourth power on a numerator. It says it's in the wrong spot. Now imagine you had a fraction and both of your factors are in the wrong spot. That says I'm supposed to be on a numerator. That says I'm supposed to be on a denominator. Move them. Notice how we basically get the reciprocal and it changes the sign of your exponents. That's true. If we reciprocate a fraction, the exponents change those signs. So a to the negative m over b to the negative n becomes b to the positive n over a to the positive m. We can do that really quickly. If you see two factors, both with negative exponents, you can reciprocate that. And it will change the sign of your exponents. Last one, kind of a neat one. Because exponents distribute across multiplication and division, this a would get a negative exponent, this b would get a negative exponent. It would say we're both in the wrong places. We would need to switch. We would need to very much do the same thing as this. But could we do it beforehand? What if we reciprocated a fraction? Then if we change it where our fraction is, it's going to change the sign of your exponent. Which means if you ever get a negative exponent outside of a fraction, you can reciprocate the fraction, altering where those specific factors are, and it would change the sign of your exponent. So x over y to the negative 2, think about that. You'd get x to the negative 2, you'd get y to the negative 2. Exponents distribute across division. That would say, I'm in the wrong spot. I should be on a denominator. Okay? That would say, I'm in the wrong spot. I should be on a numerator. So if we switch them ahead of time, you don't have to switch them later. That's the logic on, well, then you alter the sign of your exponent. So big things, the big ideas to really glean from this are exponent rules still apply. They only apply to exponents. Don't let them influence your division. When we get division of common bases, we should be subtracting exponents, but your answer will always start on the numerator. If it's positive, it remains in the numerator. If it's a negative exponent, you move it to a denominator. There is another way. I've shown you both ways here. You can also separate factors in terms of fractions and then view where your larger power is. Wherever that larger power is, that's where your factor is going to remain. Yeah, and that's a simplification idea. Next time, we'll do a whole bunch of practice on operations with exponents.